You know, when you picture nuclear power, you probably think of these massive, sprawling plants, right? But what if the future of nuclear energy is, well, small? Today, we're going to dig into a really interesting new approach that's gaining traction all over the world, small modular reactors, or SMRs for short. And we're going to see what makes them so different.
All right, here's what we're going to cover. First, we'll look at the big question SMRs are trying to answer. Then, what makes them small and scalable? We'll dive into their unique approach to safety, see how they're being proven in the real world, explore what they can do beyond just making electricity, and finally, look at the road ahead for deployment.
Okay, so let's set the stage here. If we're serious about our climate goals, the world needs a ton of clean power that's available 24/7. Traditional nuclear plants, they're great for that, but they are huge. We're talking massive projects that take years and years to build and cost a staggering amount of money. And that reality has really forced designers to go back to the drawing board and rethink the entire model.
And this really shows you that fundamental shift in thinking. On the left, you've got the traditional gigascale approach. These are custom-built giants constructed piece by piece right there on site. But the SMR approach on the right, it totally flips that script. The whole idea is to focus on these compact modules that are built in a factory with all the key systems integrated into a single self-contained unit.
So this all leads to this central question that's really driving this SMR revolution. What if, instead of just trying to build bigger and bigger, we started by scaling down? And maybe even more importantly, what if we could design a reactor where safety isn't just a bunch of add-on systems, but something that's baked into the very physics of the design itself? And that kind of thinking leads you directly to the core concepts of SMRs. So let's unpack those first two letters in the name, small and modular. This is where the practical advantages really start to pop. All right, so first let's get a clear definition. What is an SMR? Well, it's an advanced reactor that produces up to 300 megawatts of electricity. Now, for perspective, a big traditional plant is usually over 1,000. But the really crucial part of the definition is this. They are designed to be built in factories as modules and then shipped to a site for installation.
And, you know, this whole modular approach has some huge benefits. Building them in a factory, that means better quality control, and it seriously cuts down on construction time. You can scale your power plant up just by adding more modules, kind of like Lego bricks. Their small footprint also means you've got a lot more flexibility on where to put them. You can stick one in a remote region, or even use them to replace old, retiring fossil fuel plants. And here's the kicker for the finance folks. The upfront capital cost is way lower, and you can start generating revenue as each module comes online, not just at the very end of a decade-long project.
So how do they get so compact? Well, a key innovation here is what's called an integral design. Instead of all this massive, complex piping connecting the reactor vessel to separate steam generators, those components are just built directly inside the main vessel itself. And that single design choice is a game changer. It basically eliminates the possibility of the most serious type of accident you can have in traditional reactors, what's called a large break loss of coolant accident. Yeah, that integral design is part of a much bigger story. So let's really dig into what might be the most profound innovation in a lot of these SMRs, a fundamental shift in their entire philosophy of safety. Okay, so all nuclear safety is built on this concept called defense in depth. The best way to think about it is like a medieval castle's defenses. You've got multiple, redundant layers of protection. The moat, the outer wall, the inner wall, the keep. If one layer fails, another one is right there to back it up. SMRs don't get rid of this principle, they actually make it stronger.
And this is the big difference. Traditional reactors use what we call active safety. They need external power, they need electrical systems, pumps, and ultimately a human operator to intervene if something goes wrong. A lot of SMRs, on the other hand, are designed around passive safety. They rely on the fundamental laws of physics, things like gravity and natural circulation. You know, the simple fact that hot water rises and cool water sinks to cool the reactor automatically. No external power, no pumps, no human action needed.
And look, this isn't just a cool theory. This is a quote from a formal safety report, and it says that in a major coolant loss accident, the reactor core is designed so that it won't be uncovered and it won't heat up. I mean, that's it. That's the ultimate goal of passive safety, designing a system that basically puts itself into a safe state all on its own. Okay, that sounds amazing, right? But how do we actually know these passive systems will work as advertised? So let's take a look at how this new paradigm is actually being proven, moving from computer models to real-world concrete and steel.
Yeah, this is not science fiction. Right now, around the world, SMRs are actually under construction. This timeline here is for the ACP-100 demonstration project in China, and it shows real, tangible progress.
They went from site prep in 2020 to the official start of nuclear construction, the first concrete pour in July of 2021. This is happening.
And long before you pour any concrete, these designs go through incredibly rigorous testing. There are these specialized non-nuclear test facilities, like the one mentioned here, NIST-1, that are essentially scaled-down versions of the real reactor. They use electric heaters to mimic the heat from the core, and they use them to prove that those passive safety features work exactly as the computer models predict.
And just to give you a sense of the incredible level of detail we're talking about here, for just one potential accident scenario, safety experts identified and validated 21 distinct physical effects. We're talking about every tiny detail of how water and steam behave under pressure, all to make sure their safety models are absolutely spot on.
So we've established that SMRs are a new way to generate clean electricity. Okay, great. But their unique characteristics, like their size and safety profile, actually open up a whole new world of applications that go way beyond just powering the grid.
This data really helps put our total energy use into perspective. Look at this. Electricity is only about a quarter of the total energy we consume. The vast majority is used for things like industrial processes and just plain old heating. So, to truly decarbonize our economy, we have to find clean energy sources for these sectors too.
And this is where SMRs could be a total game changer. Because you can site them much closer to where the energy is actually needed, they're kind of perfect for things like providing high-temperature heat for manufacturing or chemical plants, or for producing clean hydrogen, or for desalinating seawater to create fresh water in dry regions. You could even use them for district heating, supplying heat directly to homes and businesses across a city.
SMRs clearly hold some incredible promise. But what's the path to actually seeing them deployed widely? Let's take a quick look at the final steps needed to get there.
The path forward is pretty methodical, right? First, you have to finalize and certify the designs. Step 2, you've got to get them through a rigorous regulatory review and get licensing approval. Third, you have to build and operate the very first-of-a-kind plants to prove the whole model works in the real world. And then finally, you can scale up factory production to build out a whole commercial fleet.
And look, to speed this whole process up, global collaboration is absolutely crucial. You have groups like the IAEA's SMR Regulators Forum, and they're working to standardize the licensing requirements. The idea is to make it much easier to deploy a design that's been approved in one country to another country, without having to start from scratch every single time.
So when you step back and look at it, by completely rethinking scale, by embracing factory manufacturing, and by embedding safety right into the fundamental laws of physics, SMRs are offering a whole new vision for what nuclear energy can be. And that leaves us with a final, really fascinating question to think about. Is it possible that the very smallest reactors could end up having the biggest impact on our global energy future?